In this video, I'm introducing the idea of applied optimization. So, applied optimization means that we are looking to optimize some type of a function. We've done this in linear programming, where we would have an objective function and we wanted to optimize it, find the maximum or minimum values given certain constraints. Well, now in calculus, we want to optimize functions, which means the same thing. We want to find maximum and minimum values. In Calc 1, you learned a little bit about optimization. And what you learned was that to optimize a function, the first thing you had to do was find the derivative and then set it equal to 0. And so we're going to do the same thing here. We want to set our partial derivatives equal to 0. And when we do that, we get what are called the critical points. Same thing as in your calculus class. The critical points are where our relative extrema are. That would mean the relative maximums or the relative minimums. And those are the points that we're looking for. So we want to set our partial derivatives equal to 0 and then solve those for the respective values of the variables. Now, relative extrema means either a relative maximum or a relative minimum. And the relative maximum is the highest point on the graph in that particular area, in the vicinity of that point. And the relative minimum is the lowest point in the vicinity of that point. Now, a new concept here is a saddle point. A saddle point acts as a minimum value or a maximum value depending on the perspective that you are looking at. So right here, if you were to look at this point right here, that appears to be a minimum value right in there. But if you looked at this from a different perspective, it would look like a maximum value. So once we have our critical points, the next thing that we need to do is to determine whether those critical points are relative maximums, relative minimums, or saddle points. And to do that, we use the second derivative test. Just like in calculus, when you found your critical points, you could use the second derivative test to determine if your critical points were maximums or minimums. So our second derivative test, which we call the Hessian, will help us determine if we have a relative maximum, relative minimum, or a critical point, or neither. So here's the rule. When the Hessian is positive, the function has a relative minimum at the point AB if this second partial derivative is greater than 0, and it has a relative maximum at AB if the second partial derivative is less than 0. So first of all, h has to be positive. And so here's how we find h. We find h by taking the second partial derivative of x, multiplying it by the second partial derivative of y, and then subtracting the mixed partial derivative squared. Now, what happens if h is negative? If h is negative, we have a saddle point at AB. And if h is 0, then this test tells us nothing. We don't know what we have. All right, so this is a lot of information. I wanted to get through it so we could actually get into doing a problem. So locate and classify all the critical points of the function f of xy equals x squared plus y squared plus 1. So the first thing that we need to do is find the partial derivatives. So let's find f of x. That's going to be 2x. F of y is going to be 2y. And we need to find the second derivatives of these. So that's just simply going to be 2, and f yy is also 2. And then let's find our mixed partials. The partial derivative of x with respect to y, And so that means we are taking the partial derivative of 2x with respect to y now, which is going to be 0. And then we want to find the mixed partial of y with respect to x. That's also going to be 0. So here are our derivatives. Now what we need to do is find the critical points. So to find the critical points, we take the first derivatives and set them equal to 0. So if we take 2x and set it equal to 0, we get x equals 0. Take 2y, set it equal to 0, we get y is equal to 0. So that's pretty easy, actually. We found x and y already. So we know that there is a critical point at the point 0, 0. But we're missing something. We don't know what the z value is. Because remember, we can write this function as being equal to z, the output variable. In other words, z is equal to x squared plus y squared plus 1. If we wanted to graph this in 3 dimensions, we would need to find z. So that's easy. We just plug 0 in for x, 0 in for y, and we end up with z being equal to 1. So we take that, put it over here, and we have our point. Now, the last thing that we need to do is to determine if it is a relative max, a relative min, or a saddle point. So to do that, we have to go back to the Hessian. So remember that h is equal to fxx times fyy minus fxy squared. Kind of running on a slant here. And so fxx is 2 times fyy is also 2, and f of xy is 0 squared. So 2 times 2 is 4. So the Hessian is 4. It's positive. That's the key thing here, is we don't actually care about the number. We just want to know that it is positive. And so according to our rule, if the Hessian is positive, the function has a relative minimum or relative maximum, depending on the nature of the second partial derivative with respect to x. So we have to go back and find the second partial. We have it, take a look at it. So here's the second partial derivative with respect to x, and it's positive, positive 2. So because the second partial derivative is positive 2, that means that this is a relative minimum. Relative minimum. All right, so we located and then we classified the critical points. I barely squeezed it in that little space. All right, let's try another problem. So in this one, trying to get rid of some of this stuff. There we go. So we want to find the partial derivatives of that. So f of x, try to write smaller here, is 2x. And the partial derivative with respect to x of 2xy would be 2y. The partial derivative with respect to x of 2y squared would be 0. Minus 2x would become minus 2. Partial derivative with respect to y, then the first term is going to be 0. Second term would be 2x. Third term would be 4y, and then plus 4. So I'm going to find my second derivatives a little bit later on. So I don't want to work with these right now. So what we want to do to find the critical point is set these equal to 0. So I'm going to take these two together. 2x plus 2y minus 2 equals 0. 2x plus 4y plus 4 equals 0. And what we essentially need to do is we need to solve the system of equations. We have a system of equations here. We know how to work with that. We have to solve that system of equations for x and y. We have two equations and two variables. Now you could do this algebraically. You could make a matrix out of it and solve your matrix using linear algebra, but I think this would be easy enough to do just using an algebraic technique. So first of all, let's set this equal to 2, and 2x plus 4y equals negative 4. And so if we were to subtract the second equation from the first equation, 2x minus 2x is 0, 2y minus 4y is minus 2y, 2 minus a negative 4 would be equals 6. Or y equals negative 3. Once we have y, we can find x. We have 2x plus 2y equals 2. 2x plus 2 times negative 3 equals 2. 2x equals 8, or x equals 4. All right, so we have our y value, and we have our x value. Next thing we need to do is find the z value. Now, to find the z value, we plug all these numbers into the function. Let's see what room I have down here. There we go. Just enough room down there. Z is equal to x squared plus 2xy plus 2y squared minus 2x and I think that was plus 4y. Yep, plus 4y. And so z equals negative 3 squared plus 2 times negative 3 times 4 plus 2 times 4 squared minus 2 times negative 3 plus 4 times and mistake. So this is x. We have x and y, 2y squared. I'm getting my variables mixed up. So the third term is 2y squared. So 2 times negative 3 squared minus 2 times x, which is 4, plus 4 times y, which is negative 3. And that's going to end up being equal to negative 10 once you do the arithmetic. So we have our point. We have the point 4, negative 3, negative 10. So what we need to do now is we need to classify the point. And so to classify the point, we need to find our second partial derivatives. So our second partial derivative, let's find f of xx. That's going to be just 2 again. F of y is also going to be 2. plus 4. Sorry. Partial derivative with respect to y is just 4. And then our mixed partial, f of xy. So we can go over here, take the derivative of that with respect to y, which is 2, and just to check, f of yx means we're going over here and taking the derivative with respect to x, which is 2. So they are the same. And so h is going to be equal to f of xx, which is 2, times yy, which is 4, minus the mixed partial, which is 2, squared. So 8 minus 4 is 4 again. And so that is positive, which means it's a relative max or a relative min. And so you go to the partial derivative with respect to x. It is positive, so that means that this is going to be a relative minimum point once again. All right, I think this video is long enough. That's a couple of examples to get you started. Go through the rest of the examples that are in my notes and watch some of the other videos that I've posted and have fun.